into some other interesting things which were related. So the second topic, and a much bigger one, is how things drink. So we expect, again, when things get small, they're going to use surface tension in interesting ways. So this is a PhD of a student, Wonjong Kim. So there's not even much data on how the water uptake scales with the body size. So there's some for mammals, some for birds, nothing really on insects, so we don't even know the extent to which they uptake water. But there are many different styles of drinking used in in nature. So one is capillarity. So here you can imagine there are a lot of tube drinkers, so hummingbirds, and use capillary action. You can also have entrainment of fluid. So here dogs, their tongues actually go like this, if you know, and they actually ladle fluid up. And cats basically hit the surface and entrain fluid through inertia and then snap off some volumes. So these are not too different because there's some captured here and some captured actually beneath it. But this is basically using inertia. And then there are things which use osmosis, and we're going to see that there's some that use contact angle hysteresis. But the great majority of things just apply, like when we drink, we apply a suction pressure which draws in fluid, right? So the question that arises, which of these are not well understood and which of them depend on surface tension? And chances are that the ones that depend on surface tension are not going to have been considered too carefully. So these are, again, so different. If we have tube drinkers, then you can apply suction pressure, which is basically muscular, or you can use surface tension. And then we can have dipping. So we've seen this entrainment problem, the Landau-Lewis-Derjagan problem, where you basically pull a plate or a fiber from a fluid bath. That's used by a lot of creatures. They basically dip. So they have the insects have a tongue which they dip into the fluid, and they entrain fluid through the action of viscosity and surface tension. You saw surface tension is also important here, right? And so then there's this the high Reynolds number end of things which is not so dominated by surface tension. But so really what we want to do is classify and rationalize all drinking styles, which is a rather ambitious project because there are many different types of creatures. But nevertheless, so we start breaking things down. So the scales, if you have, we can look at the scales of the forces. So basically there's going to be, if there's an applied pressure force, delta P, then this is the characteristic force that can be applied. So it's going to depend on the size of the creature. Then the inertial force. So these are forces causing motion. So we have this we can have this pressure coming either from muscular pressure or from a curvature pressure. So with surface tension as its origins. So these contribute to the driving force. And then the flow is going to be resisted by the fluid inertia, which is going to scale like this, by viscosity or by gravity. Okay. So again, the relative importance of both the two driving forces or the three resisting forces is going to depend on the scale of the creature, right? So we know very small things rely on surface tension, very large things don't care about surface tension. Okay, so here we can plot all of the different creatures for which there is data. So the Reynolds number as a function of Reynolds number and Bond number, and we can color code according to their drinking style, right? So we can then hope, so basically where Reynolds number is low, viscosity is going to be important. Where Reynolds number is high, inertia is important, so such is true for big creatures. For Bond number less than 1, surface tension is going to be important. For Bond number greater than 1, gravity is more important. So basically, most of these creatures use surface tension in some way. So down here, and these guys are not so concerned about it. But there are a few exceptions. We'll see these guys and these guys do, their drinking technique does rely critically on surface tension. So what we want to try and do is rationalize the different styles according to the morphology of their drinking parts. Okay, so here's something, our first look here was at something which used contact angle hysteresis. So this is something, did I mention this one before, did I? Yeah. So these guys use variable wetting properties to trap air, to trap water from mist. So they have these hydrophilic bumps, which causes the drops to nucleate, and then they grow by accretion until they get large enough to be blown off by the wind, and so then they're blown into the hydrophobic valleys and then consumed by the creatures. And this has been used, the development of these so-called superplastics, for water gathering in the third world. So they have sheets of this stuff. They put it out in the morning, and they collect water. Okay, but this is our this is the fallow. It uses surface tension contact angle hysteresis. So it swims in a circle, generates a vortex which sweeps up its prey. And its prey is captured in drops. So you can see to move the drop, it had to do this. And this is used, so it's probably worth seeing this again, but so it's basically capturing a drop in its beak and then moving the drop up by doing this. Okay? And this is used by a lot of creatures that live in sort of shore areas, and they have sort of long, thin beaks. And so what's actually going on? So here you can see the drop with its prey suspended in it. And so the question is, how do they take in water? So they can't just apply suction. If you're using a tube, you can apply suction, but they have an open beak. So applying suction is going to do nothing. Obviously, gravity can't help you because the drop is moving against gravity. And so Rubega looked at this problem. They noted that it must be surface tension, but they didn't exactly say how. They suggested that maybe it was like capillary rise, right? But does capillary rise work in the beak geometry? Not clear. So, but we can answer that. So again, so they basically draw up their prey, they grab the prey, and then they expel the water. And they basically do this 3 times per cycle. So in order to move the drop from the tip to the mouth, they have to move, they have to open and close it 3 times. So this is, I haven't shown, you guys haven't seen this, have you? Yes. No. Okay. Okay, so this is, I like this story because this is a great warning for those of you who do theory without doing experiment, right? Because I thought, I can solve this problem, right? Capillary rise along a plank. So if you do this, you say, okay, here's our beak. This is our bird beak. And we're going to look at the possibility of there being spontaneous motion of this drop from the tip to the mouth. So in order to do that, all we have to do is to write down the surface energy. And if gravity is negligible, then you say that this thing is a catenoid, right? So that's going to be the shape that minimizes the surface energy. And so you basically can look at the surface energy of the whole system as a function of x, right? And so if you do that, then you know that the force acting on the drop is the gradient of that surface energy with respect to x. So it's simply the surface tension times the gradient of this area as a function of x, right? So that's a problem that one can solve. So if you solve that, then you get this criterion for drop motion in terms of the geometry of the plate. W being the thickness, H being the opening angle. And you have an additional requirement for drop stability. So if the plates are too far apart, then the drop will break. Okay? So if you consider these two taken together, then you have this criterion for spontaneous drop motion. And it says simply this, that the thing it boils down to this. So basically the beak has to be long and thin. So the ratio of the length to the width times the tangent of the opening angle has to be greater than the square root of 2 pi. Which is kind of interesting, right? And I thought, That's why these beaks all have very long, thin beaks. But is this meaningful? So there I was thinking that I had actually done something useful that would inform nature. And then you go into the lab, and so here we put, these are our bird beak nose pliers. These are about to scale, so this is about 5 centimeters long. And we put silicone oil down these are stainless steel, and the silicone oil wets stainless steel, so it wants to go in this direction, and it moves spontaneously. But what happens if we use something a fluid which has the same wetting properties as does water on the beak of a bird? So the beak of a bird is basically made of keratin, which is like what your fingernails are made of. And so if you use water, it gets stuck, right? And it gets stuck because of contact angle hysteresis. Exactly the same reason why a raindrop gets stuck to a window pane, right? So this is a disaster. So basically I've noticed that my theory didn't have contact angle hysteresis in it. And so that criterion I had is completely valueless. So how do these birds get the thing to go? How do they overcome contact angle hysteresis? They do so by making the situation dynamic. So they basically open and close their beak in such a way that you break the symmetry and allow the drop to move. So So we're going to optimize, but first you can see basically how it moves. So it's basically, when it closes it exceeds the contact angle fastest on the right-hand side. So let's just try and rationalize that. So, okay, so we know that these static contact angles are bound above by the advancing value and below by the retreating. And we also know there's this lateral force balance on the static drop. So basically, again, if this thing is going to be sitting there and there's no net force acting on it, because they're joining at this angle here, these two angles have to be related through the opening angle of the channel. Okay, so that's just a geometric fact that you get from force balance on the drop. Okay, again, we're assuming this is 2D, and so then you have a continuity which ties everything together, but you can basically invert this to get theta 1 and theta 2 in terms of the position of the drop, the volume, and the opening angle. Okay? So what we're going to see is when we close this, because theta 1 is always greater than theta 2, when you close it, this reaches the advancing angle before this. Right? So you close it, this thing hits advancing angle, so it starts moving before this one does. So you want to close it, so this one moves to the point where this one starts to move, then you want to reverse direction. And then when you reverse direction, they're both going to want to go like this, right? So let's just be clear about this. As we close it for the first time, both of them are going to want to go like that, right? But this one, because of this constraint, hits the advancing angle first, so it starts moving, right? Before this one does. And so then you want to stop before this one starts moving. And then when you're opening, these are so you're opening, so these are both going to go like this, right? But because of this constraint, this reaches the receding value fastest, so it starts moving. Okay? So you break the symmetry, and so you get this ratcheting motion. So again, you have this asymmetry coming from the force balance. And so anyways, from this formulation, you can basically find the critical opening angle at which this thing will start moving. Right? And you can also find the angle at which this one will start moving, advancing, and you don't want that to happen. So you want to basically always cycle between these two angles. Right? And so this is basically what you see here. This is in the closing phase, you want to be between these two angles so that this one will move and not that one. And then in the opening, when you open, you want this one to move and not this one. Okay? So you see this asymmetry, which is coming from the contact angle hysteresis. Right? So it's a combination of the contact angle hysteresis and this geometry. Right? But you can then tune it and say what are the optimal angles, and so you basically want to run here, right? So you basically want to push things to the limit and get as much bang for your buck as you possibly can. And so we did a series of experiments, so we can see if we close. So this is the closing angle. If we open the beak too much, of course, the drop will break. If we don't move it enough, the drop will just stay pinned. But there's this intervening region where we have this ratcheting motion, and it's basically optimally tuned here. So you can basically get, in 3 cycles, you can move the drop from the tip to the mouth of the bird. Okay, and so here, this is sort of more or less optimally tuned. And that's basically what it looks like when the bird does it. So it's kind of, I think it's an interesting, I think it's a very interesting story because for several reasons. One, it makes clear how important wetting properties are for feeding these creatures. And there are lots of creatures that use this. We know that of many in the bird family, but there are probably other creatures that use this as well, right? And if you change the wetting properties of their beaks, it's going to be impossible for them to feed, right? And so, and the other thing from a physical point of view, it's interesting that they're actually using contact angle hysteresis in combination. Usually we think of contact angle hysteresis as something to overcome. It's a pain because it causes drops to stick. But here they actually use it in conjunction with this complex, with this wedge geometry to generate propulsion. And so this is the first. I presented this to some engineers, and one guy goes, I knew it had to be good for something. But again, if something is good for something, then nature will find it. Right? Okay, so that's contact. Those are examples of contact angle hysteresis being used for drinking. More commonly, there are many creatures that drink through tubes. So mosquitoes, elephants. And the fluid rises through some combination of applied suction and capillarity. Okay, and again, it'll be resisted by some combination of gravity, inertia, and viscosity. So which of these forces is most important will depend on the scale of the creature. And we did a complete treatment of capillary rise in tubes, so this will all be very familiar to you. We also did entrainment, which will be another story. But okay, so this is something, if this hasn't come up in the course before, you should always remember this. The force that can be generated by creature scales is its cross-sectional area. Okay? So this is saying the force that can be generated goes as its mass to 2/3, so it's length scale to the second power. So if we plot this is borne out by the weightlifting world records. So this is the weight lifted versus the logarithm of the weight lifted to the logarithm of the mass of the man. You can see that this has a 2/3 slope, and we can, on the basis of this, deduce who the strongest man is, and it's this guy here because he's slightly above the line. Right? There's actually a way of normalizing measure of strength. Okay? And so, if this is true, which we have every reason to believe, then the pressure that can be generated by a creature is independent of size, because you expect the pressure to be the force divided by a characteristic area. So is this actually true? This is saying that the suction force generated by any creature is going to be about the same. And if you look, it actually isn't bad. So elephants and bees, the same. Mosquitoes, factor of 2. Humans, factor of 5. So the largest variation, so the largest pressure that can be generated is bed bugs, and these things are known for being nasty and feeding on blood, ingested blood from animals. But in any case, you see that the characteristic pressure, suction pressure that can be generated by any creature is around 1/10 of an atmosphere. Okay, so that's kind of nice that there's just one number which describes this. So we can then use that one number, then compare it to capillary length, right? So this delta P we've decided is the same for all creatures. And so if we compare the characteristic capillary suction to, applied suction to capillary suction, then it's going to look like this. Right? And so there's going to be a scale, that is to say, there's going to be a tube size at which capillary suction becomes more efficient. Okay? So then we can look to see which is the source of resistance, whether it's gravity, surface tension, gravity, inertia, or viscosity. Okay, so this is a thorny devil lizard which ingests fluid. So it's drinking right now. It just sticks its leg in the water, and water wicks up through capillary action. Okay, so its skin, as you can see, has a sort of fine network of fractures, and water is drawn spontaneously up into its mouth. Okay, and so this is important because it lives in a place where, for example, it'll often get water drops that are in the morning on plants, and it'll rub up against the plant, or if there's a moist ground, provided the texture of his skin is smaller than the texture of the soil, then the water will wick up spontaneously, right? And so this is something which uses capillary suction for drinking. But more generally, we can look at we've derived this equation in class. So this is the force balance. We can, so here we have the applied suction, and this is capillary pressure, and then this is resisted by inertia, gravity, and viscosity. Again, we derived this in class, so we can non-dimensionalize and then look and see for every particular creature what the relevant forces are. Okay, and so for large creatures which use inertial suction, so this term dominates this. We basically just have a balance of the suction pressure and inertia, and that gives us a speed which basically goes like this, a very simple scaling. And that's basically what's used by all of these guys. Okay? And that rationalizes that data. So elephants, humans, camels, yada yada. And then when things get smaller, so mosquitoes, butterflies, bees, hawk moths, again they use suction. So you may ask, why don't mosquitoes use capillarity? Well, actually, once you've filled the tube up, you're no longer using capillarity, right? Right. So they basically fill up. They may use capillarity to fill up their proboscis, but then they apply suction, and it's resisted principally by viscosity. So you see then this scaling emerging. So the velocity going with the applied pressure and scaling with 1 over the viscosity. And so you can see that predicts the Reynolds number going as Bond number to the 3/2, so ants, bees, butterflies, all sorts of things. So that provides rationale for that data. And then capillary suction. So when things are small and are not filling up their tubes completely, so for example, hummingbirds stick their tongue in, as we'll see, and fluid fills their tongue, and then they withdraw the tongue, unload it, and they do it again and again. So when this is true, then you have a balance between the capillary pressure and viscosity, and we've seen Washburn's law already in class, right? Basically the front speed going as time to the 1/2. So these are all scalings that we've derived already, but they're just applying them to this in this biological context. So this is the hummingbird. This is Sherbrooke, who's a friend of ours. He's very comfortable with the hummingbirds. But you can see, on the right, so watch the tongue. So there's dye here. You see the dye shoot up, right? I shouldn't say, but there's some, well, I won't even go there. But in any case, you can see basically the fluid goes up and then it withdraws its tongue, it unloads, and then it dips again. But it's basically loading through the use of capillarity. Okay, and so now that basically allows us to rationalize all of those creatures that that use tube drinking. Now, we're thinking specifically of water. There are also a lot of creatures that feed, so they not only drink but feed on nectar. So this is their principal source of energy. And so they basically get this from flowers. Flowers attracts the creatures by offering them honey, nectar, and so then they in exchange they pollinate the plants. So there are three basic mechanisms for nectar drinking. So first is active suction, where you apply a suction through a tube and draw nectar up. So this is used by ants, bees, butterflies, and moths. And then there's capillary suction, where you have so this is used by honeyeaters, sunbirds, hummingbirds. They basically, as we just saw, dip their tongue in and fluid is drawn up spontaneously. Then they unload the fluid and continue elsewhere. And then there are some ants, bees, and bats which use viscous dipping. So they dip their tongue into the nectar and then withdraw it. Okay? And so this is kind of an interesting problem. We'll first look at, so it's something that one can pose mathematically as an optimization problem, right? This is why I like it. But okay, so these are our experiments. We basically look at a honeybee, and we have a pool of nectar from which it feeds, and you can see, so this viscous dipping, it basically dips its tongue in, withdraws the tongue, and there's some volume of fluid entrained, which you can see here. It also has some sort of texture which enhances the volume entrained. But basically it's dipping its tongue into the nectar and so entraining it in that fashion. Okay, so again, so if you look, so there's a huge volume of data in the biology literature indicating the dependence where they basically measure, they take, say, a bee, and they put the bee in front of a dish of nectar, and they measure how much it drinks in a given time. Okay, and so they do this for the same creature in front of different concentrations of nectar. Okay, by measuring its change of weight, they can measure the volume flux, and from the volume flux, if they know the concentration of nectar, they can see how much energy it's getting. Okay, so they can then assess experimentally what the optimal concentration is. Right? So for what nectar do they receive the most energy? Okay, so what they find is that for these three different techniques, there are three different answers. For suction, for active suction, it's around 35%. It's actually 35-40%. Same is about true for capillary suction. Okay? But for viscous dipping, it's higher. So the optimal concentration for creatures that use viscous dipping is higher than for those which use suction. Okay? But you can see it basically, we can classify the optimal concentration on the basis of drinking style. Right? So basically for the suction drinkers, it's one value between 35 and 40, and for these guys, it's around, for viscous dippers, it's around 55%. Okay, so this is, again, I think, interesting in that it can be posed as an optimization question. So just think of it this way. If you're a tube drinker, you know that the goal is to get as much energy as you can as quickly as possible, right? So you have to spend as little time feeding as possible. So if you take fluid up, if you're drinking nectar, you know that the higher the nectar concentration of sugar, so the higher the sugar concentration, the greater the energetic reward, right? So if you can take in the same flux of a nectar with higher sugar concentration, you get more energy, so it's better for you. The problem is that viscosity of the fluid goes up exponentially with sugar concentration. So there's an energetic penalty to drawing up very sweet nectar. Okay, so you see here the relation is sort of a bit of a mess, but basically the viscosity of nectar increases exponentially with nectar concentration. So we can write down the volume flux, and what you want to do is maximize this energy flux. So Q is the volume flux, S is the concentration of sugar. and A is basically the area of the tube. So, so you can say, okay, let's try and calculate the optimal concentration. So we basically have to evaluate what this is and see what its derivative is with respect to S. Right? And so but we need some constraints. I mean, as a general statement in biology, we always think that nature has evolved to be as efficient as possible. So we can pose it as an optimization question, but it's never entirely clear what's being optimized and what the constraints are. For a well-posed mathematical optimization problem, you need some constraints. So what Kingsolver did, he had this very nice idea of trying to pose it as an optimization problem, and so he assumed that what was held constant was the pressure difference. So if you assume that, then you find from this relation simply that Q goes as 1 over mu. So if you substitute Q for 1 over mu there, and then you substitute this mess in for S, you find that the optimal concentration is around 21%. So this is saying that E goes as S over mu. So then, again, you have to use this awful thing. But then you find that the optimal concentration, that is for which this has a maximum, is 21%. And this is low. It's not consistent with the data. But if you assume that what's held constant is the rate of work, such as we see here, then we expect Q to scale like mu to the minus 1/2 power, and the E prime then to scale like S over mu to the 1/2, and it predicts an optimal concentration of 33%, which is roughly consistent. We saw it was about 35% for these suction drinkers. So we can rationalize all of this data simply by saying that what's being optimized is the energy flux, and what's being held constant is the rate of work. So if you say that the rate of work being done is constant, and they're trying to optimize the energy intake, then we can rationalize 33%, which is not far from what one sees. And then viscous dipping, so we should be able to do the same thing here. So there again, we saw in class what the thickness of a layer is, of a coating layer, and we saw that in the low bond number limit, it looks like this, capillary. So it goes as the tube size times capillary number to the 2/3, where again capillary is viscosity of the curvature. So if we this is basically the power required to overcome the viscous dissipation. So it's suggesting V is going as mu to the minus 1/2, mu being the viscosity. So the volume flux we can write in this fashion. So again, we've seen that E scales as capillary number to the 2/3, which is where this scaling comes from. And so we see that the energy flux is going to scale like this and this. So if we optimize this with respect to S, we ask what S maximizes this, we find an optimal concentration of around 52%. So that actually allows us to rationalize all of the viscous dipping data. And so this is data from all of the creatures reported in the literature. So you can see there are many of them, and they all fall along these lines. So the ones that use active suction or capillary suction are along here. The ones that use viscous dipping along here. Okay? So it's kind of I think it's a nice example of trying to pose a biological problem in terms of as an optimization problem. Of course, the problems have to be relatively simple. So because things get, for example, in looking at that bird beak, this one here that we just looked at, is that bird beak optimized for what it's doing? Well, maybe, but then again, they also use beaks for combat, for mating, for whatever, so you never really know what's going on. Here's a situation where they have tubes. The tube principle, it seems that the only role of the tube is to take in nectar, then one can perhaps hope to make some headway. But again, a general rule in biology is also that things are always more complicated than you think, so one should try to be modest with one's claims. But nevertheless, we see here that this relatively simple model has allowed us to rationalize the observed optima for this active and capillary suction as well as these viscous dipping. And so the guiding light, so basically what's being optimized is the energy flux subject to the constraint of constant power output from the creature. Okay? So in the last few minutes, I'll just mention a couple of quirky things. I think we've seen capillary origami where you have, you can put droplets on flexible solids. So imagine this is a piece of wax paper or something. If it's flexible enough, then the surface tension forces along the edge can bend it, right? And the water's evaporating, which is why the thing is closing, right? And so, but this only works. Notice that when we put this drop on this sheet, surface tension has to not only cause the flexure of the sheet, but it has to overcome gravity, right? Because gravity wants to keep things on the ground. So that's basically putting an upper bound on how big this system can be, basically. And so what's that scale? That's going to be the capillary length, right? So surface tension has to overcome gravity. But that's why all of these things are very small. This is a millimeter scale. But in general, in order for surface tension to overcome the elastic stresses associated with bending, we simply we need to have a sheet which is large relative to this elastocapillary length. Okay, so H is the thickness of the sheet, E is the Young's modulus. Okay, so again, if the sheet is large enough, then the bending cost is less, so you can expect the surface tension to bend it. But in order for this to happen, here where you have a fluid drop, surface tension has to overcome gravity, which means you have to be small relative to the capillary length. Okay? But you can get around that by getting rid of the fluid and just having the interface, right? So we know that we can do that with bubbles. So if we do bubbles, this is now quite large. So these are centimeter scale things. We basically generate a huge bubble, we put it down, and that will cause flexure of the solid. And so that was just discovered by some friends in Paris, José Bico and Benoit Romand. And one thing I like to do is, whenever someone discovers something which I think is interesting, look for the equivalent in nature, because the guiding light is that nature always got there first. So these are examples which we've looked at of capillary origami in nature. So this one we've touched on briefly, folding of flexible flowers. So it turns out the spider capture thread is also it's an elastocapillary problem, and also the tongue of the hummingbird. So I'll just quickly go through these. So the flexible flower we've seen basically sits at the interface, and when it floods, when the water level comes up, the thing closes in response to hydrostatic pressures, and surface tension keeps it from flooding. Okay, and so that's the basis of this little design which we've seen. So this is an example of capillary origami in nature. So it's basically solids being deformed by interfacial forces. And we turn this upside down. And so we turn it upside down. We generate, as we lift up, we get a rho GZ suction, which causes the thing to close. And provided the petals are close enough together, if they're well cut, then the only thing which keeps air, surface tension will keep air from intruding into the suction region, right? So the thing basically zips shut, and you can grab water.
So this one can be bigger because it's upside down?
No, they can both be. There's no asymmetry. It's the same. Symmetric up and down.
You have to overcome gravity?
No, the same is true. Well, the other one, you basically pull down, and so water wants to get in, and surface tension keeps it from coming in, right?
No,
so there's.
I mean, the origami case, you said that this
Oh.
is harder because.
Oh no, so here you can go larger than capillary length, but you can't have the gap between the two has to be less than the capital length, right? Because here, surface tension is simply keeping the thing from flooding. Yeah? Okay, and so the spider web, if you look at a spider web, there's these are basically, the radial threads are basically structural, so they keep the thing in place, but these are capture threads. Okay, so these capture threads they're designed for catching prey. Okay? So the radial threads are sort of stiff and dry, but these capture threads actually, so this is the radial thread, and this is the dried capture thread. But the capture threads are actually in fluid, which looks like this, right? So the reason for this is that when prey hits, it's wet, so it sticks, right? Second of all, it damps the impact. So as this thing flies in and hits one of these capture threads, the thing stretches, right? And there's a lot of dissipation because you're basically uncoiling this elastic thread within a viscous fluid. So basically, because if it was perfectly elastic, it'd go whoomp, whoomp, right? And come out exactly the same. But here it goes because you're unraveling these elastic threads in a viscous fluid. Okay, so those are the two effects of this capture thread. One is it's wet, so the prey sticks to the thread. Secondly, it takes energy out of the impact. And so one can see that there is a sort of a spacing of these drops, which looks like this. Is it Rayleigh plateau? The chemistry of this stuff is nasty, by the way. Yeah. Right. So anyways, we did a little experiment with this, which is kind of fun. So here we have elastic coils. So we basically look at Rayleigh plateau instability on the elastic coils, and so basically you have to look at to get the spacing of the threads of the drops. You need to look at the elastic energy as well as the surface energy. Anyways, that's it. We're out of time. So, but this is I think a sort of a rich theme, and there's many problems as there are bugs. So. Keep your eyes open. There are always very interesting things in nature. If you see something which you're interested in, send me an email. I'd be happy to hear about it. But there are again infinite number of problems, and not many people that know as much about surface tension as you guys now. So you can probably be the first to solve them. Okay, so thanks for your attention. So next class will be on football. So. Not exactly surface tension. I'll try and work it in somehow, but and I'll get your problem sets back, and then it will be carnival time.